Good morning. This is your stats sensei, Mr. Spensei, and we are going to continue on with two sample proportions. This is the exit ticket, and the exit ticket is tied to the exact same problem set that we were working on this morning for the warm-up. The warm-up was shift happens. We had a large company with two shifts. This says has more than 2,000 workers. This should say creates more than 2,000 parts. So I'm going to go ahead and make that change. And they must meet the same specification, and we have the data here. And we're gonna go ahead and start filling this out for the confidence interval. And it said the day shift, 188 of its 200 parts meet specifications. So this right here, I'm going to call this the day shift. This is 188 out of 200. So I can figure this out, 188 over 200. When I divide that out on the calculator, 188 divided by 200, I end up getting 0.94. And for the night shift, and by the way, I'm going through this fast, and you can watch the other video to get the more information. For the night shift, it was 180 out of 200. So 180 out of 200. And when I divide that out, I'm going to get 90%. All right. So that's my difference. I'm going to go ahead and write my formula. P hat 1 plus or minus, not plus or minus, P hat 1 minus P hat 2. I should start over. P hat 1 minus P hat 2 plus or minus Z star P hat 1 times 1 minus P hat 1 over N1 plus P hat 2 times 1 minus P hat 2 over N2. It says use a 96% confidence interval to estimate the difference in the proportion of parts produced within specification. So we're going to use a 96% confidence interval. So this is 0.96. And we know we're going to go to an inverse norm. And our area is 1 minus 0.96 divided by 2. So second vars, inverse norm, parenthesis, 1 minus 0.96, close parenthesis, divided by 2, mean of 0, standard deviation 1. And we need to start at the left. And when I do that, I end up getting a negative 2.0537, but we want to be positive about things, so we're going to use the positive value. So this is going to be 2.0537, and that'll be our positive value. I'm going to go ahead and run this thing and plug in and do all that work, and then we'll come back and write the conditions, because I need to make a big deal about the conditions. The conditions are really important, and they're different than a hypothesis test. So if I'm plugging in, I need P hat 1. Well, P hat 1 is 0.94. So 0.94 minus P hat 2 is 0.90. Plus or minus Z star is 2.0537. And we know we're going to be over N1, and N1 is 200. And this is P hat 1. Well, P hat 1 again is 0.94 times 1 minus that is 0.06. 1 minus P hat plus 0.90. That's P hat 2. 1 minus that is 0.10. 90 minus 1. And then that's over 200. That should be a 0.90. So let's go ahead and run this test. Stat test. We're going to scroll all the way to letter B, which is 2 proportion Z interval. We had 180 pieces that met specification out of 200. in the day shift and 180 out of 200 in the night shift. And we're going to run a 96% confidence interval. But when I do that, I end up getting negative 0.0156 and 0.0957. Negative 0.0156 to 0.09557. So there's my interval. I'll rewrite that. Negative 0.0156 to 0.0955. I only need 4 places. All right, so this is my lower bound, this is my upper bound. As we see, we can see that 0 is contained. Because 0 is contained, we can't say at the 96% level that there's a difference in the proportion that meets specification. All right, our conditions. So I'm going to make this my day shift conditions, and this my night shift condition. When I go back and look, it says to investigate the belief a random samples. So this right here tells me I have more than one random sample, and one is of size 200, and the other size of 200. So we have random sample. Of 200, and that was given. And next we have, for the night shift, we also have a random sample of 200, and that was given. So both of those take care of meeting specification. Here we have, and then the next thing is independence. Well, we have 2 independent samples. 2 and I can go ahead and say the same thing over here. 2 independent samples. The next thing, n is less than 10%. So n equals 200. It does that for both of them. We multiply by 10, and we end up getting 2,000. And that's less than the 2,200 that we said was the population. Over here, n equals 200. 200 times 10 equals 2,000, and that's less than the 2,200. So in both cases, it's okay to sample without replacement. And by the way, the first 3 are exactly the same as the hypothesis test. So 1, 2, and 3, those are no different than a hypothesis test. But number 4 is different, because on the hypothesis test, they use n p hat c, and we're going to use n1 p hat 1, and n1 times 1 minus p hat 1. And they're going to use PC. And over here, on this one, we'll go n2 times p hat 2, and n2 times 1 minus p hat 2. And instead of p hat 2, they'd be using p hat c. Well, what did we say p hat 1 was? It's 0.94. So this is going to equal 200 times 0.94. When we multiply that out, I find out that that's 188. That's greater than or equal to 10. We're good to go. Here, it's going to be 200 times 1 minus 0.94, and that equals 12. And 12 is also greater than or equal to 10. Close, but still works. The next one is our sample size is 200, and it's 200 times 0.90, which is 180, which is greater than or equal to 10. So that's good to go. And then it's 200 times 1 minus 0.90, and that equals 20, which is also greater than or equal to 10. So in this case, we know the sample sizes are large enough. All right, so please note, there's a big thing that I really want you to get, as 1, 2, and 3 have the same conditions as the hypothesis test, but number 4 is different. The hypothesis test has p hat c, and the confidence interval has p hat 1 and p hat 2. All right, I hope this helped, and I hope to see you on the next one. Thank you.